But again, we want to think about how we can simplify these. On our next example, let's go ahead and look at solving for x in the expression square root of 5 to the x equals 125. Usually the key to solving these is trying to get like bases. So rewriting our like bases here, I get 5 to the x halves equals 5 to the third. Now that I have like bases, this implies that the exponents must be the same if I have equality. And of course, solving algebraically, I get x equals 6 here. And very easily you can plug 6 back in here. 6 halves is 3, 5 cubed is 125, so that works out pretty slick. Okay, let's go ahead and look at solving another one for x. This one, we're going to have b squared quantity to the x plus 1 equals b to the negative 6. Now, I kind of have like bases here, they just need a little bit more work. First of all, remember the rule, when you raise a power to a power, you multiply the powers. And the trick here is to remember to distribute the 2. So here we have b to the 2x plus 2 equals b to the negative 6. That implies that 2x plus 2 equals negative 6. X plus 1 equals negative 3, dividing through by 2 leaves me with x equals negative 4. And of course you can check this by plugging back in up here. Negative 4 plus 1 is negative 3. Negative 3 times 2 is negative 6, which matches what we think it should. Now we finally get into a little bit of calculus. We're going to be looking at the derivative of b to the x. And of course, when we start talking about the derivative of b to the x, we're going to bring in the natural number e, and we're going to make the base equal to the natural number e. So we'll be talking about the derivative of e to the x and the derivative of e to the u as well. So first of all, the derivative with respect to x of b to the x is equal to b to the x natural log of b. Always put parentheses around the arguments of your log function so they don't get confused with any other part of your expression. Let's go ahead and look at then the derivative of e to the x. This would be e to the x natural log of e. But we know that the natural log of e is 1, so the derivative of e to the x just is e to the x. And that's really nice. That's an easy one to remember. Now this is only if the exponent is just x. If the exponent is anything else, this is going to be a little bit more complicated. So let's go ahead and look at the derivative with respect to x of e to some function containing x. Well, this is just going to be equal to e to the f of x times the derivative of that exponent. Now another way to say this would be kind of with our u substitution notation. The derivative of e to the u is e to the u prime, and you're definitely going to want to have these memorized. Let's go ahead and look at an example using the derivative of e to the x. So let's look at the derivative with respect to x of e to the 2x cosine of 3x. So first of all, I see right away that we have two functions being multiplied together, so that should bring up in mind the power rule, or sorry, the product rule. We'll also be using the e to the u and the derivative of our trig function as well. So product rule. We have the first times the derivative of the second plus the second function times the derivative of the first function. Now we haven't taken any derivatives yet. We've kind of just shown our work and kind of set things up a little bit. So from here, drag along the e to the 2x. I'm on this piece right here. The derivative of cosine 3x, the derivative of cosine is a negative sine 3x times the derivative of 3x, which is 3. So the derivative of cosine of 3x is negative 3 sine 3x plus cosine 3x times the derivative of e to the 2x. The derivative of e to the 2x is e to the u times the derivative of u, which in this case is the derivative of 2x, which is 2. So there is my derivative. Now this is the slope of the tangent line at any point along the graph. I could do curve sketching, slope charts from here, etc., but this is my derivative. Of course, we're going to want to clean this up a little bit for full credit. That would have given me my 9 points right here on a test, but we want that last point, so let's go ahead and clean it up. For our final answer. Okay, factored completely. Okay, let's go ahead and look at another example as well. Okay, this is kind of going to be a long one. So let's look at the example where we do the complete curve sketch. First, second derivatives, find critical numbers, possible points of inflection, the whole deal. Domain, range, intercepts, everything. Another way to think of this function is x over e to the x. So in this first form, you would be using a product rule to find your derivatives. In the second form, you're going to be using a quotient rule. And it doesn't matter which form you choose, just choose a form. First of all, let's go ahead and note that we have a horizontal asymptote at y equals 0. We have a horizontal asymptote at y equals 0 because if we take the limit as x approaches infinity of x over e to the x, we will get 0. You need L'Hopital's rule for this, which you may or may not know yet. We'll be learning about it in the next week or two. But trust me on this one, there's a horizontal asymptote at y equals 0. We also have a domain issue. If we look at the domain, I can plug in anything I want here. There's no restrictions. There's nothing that's going to make the denominator undefined. And let's go ahead and look at the range as well. Now, with the range, we may not really know right now what values we can get out of this. So I'm going to leave the range until after we do the curve sketch to see what we get back out of this. Let's go ahead and look at the first derivative. If you find the first derivative either using the product rule or the quotient rule, I'm going to go ahead and use the product rule. I will use the first derivative and a slope chart to determine critical numbers and whether my graph is increasing or decreasing. So that's what we have here. So let's go ahead and look at our first derivative. I'm going to use the product rule. So I have the first times the derivative of the second. The derivative of e to the negative x is negative e to the negative x, plus the second times the derivative of x, which is 1. Now looking at this, it's kind of hard to determine critical numbers, so this is why I really emphasize a lot to simplify, simplify, simplify. Because if we factor out an e to the negative x here, I'm going to be left with 1 minus x. And of course this can be rewritten as 1 minus x over e to the x. And then from here it's really easy to tell exactly what my critical numbers are. So critical numbers. Critical numbers occur when our first derivative is equal to 0 or is undefined. So what makes this equal to 0 is if I have a 1 in the numerator, so therefore x equal 1 is a critical number. And there's no value that I can plug into the denominator to make the denominator equal to 0, to make the fraction undefined. So e to the x, remember the graph of e to the x, it never crosses the x-axis, so it can never be equal to 0, so it can never be undefined. So x equal 1 is a critical number. Now what I do is I take this critical number and I plug it into a slope chart. The slope chart should give me an idea of whether my function is increasing or decreasing, and if I have any relative extrema. Remember, with the slope chart, we're basically looking at the behavior of the first derivative. So I plug in values to the right and to the left of this critical point into my first derivative. So if we plug in 0 into my first derivative, I get 1 minus 0 over e to the 0, which is positive. If I plug in a 2, I get 1 minus 2 over e squared, which is negative. So this tells me my function is increasing to the left of my critical number, and it's decreasing to the right. So this point, x equal 1, is a relative max. Now if I take this point 1 and plug it into my original function, I get 1 over e back out. So this ordered pair, 1 over e, gives me my maximum point on my graph. So if it's my maximum point on my graph, I can expect that that's also going to be the limit for the range on the upper bound. Next we want to look at the second derivative. Now with the second derivative, of course, I'm going to get information here about possible points of inflection, PPIs, and concavity. When I take my second derivative, let's recall f of x is equal to x e to the negative x, And then I had a lot of different forms for my first derivative. One form I had for my first derivative was e to the negative x times 1 minus x. Another form was for my first derivative was 1 minus x over e to the x. And again, simplification makes finding these derivatives easier. So I'm going to go ahead and use the product rule again off of this first form, but you could use the quotient rule here as well. So my second derivative is going to be the first function times the derivative of the second plus the second function times the derivative of the first. The derivative of e to the negative x is negative e to the negative x. And of course we're going to want to simplify this a little bit. I can pull out a negative e to the negative x, and after I do that, actually let's pull out just an e to the negative x, and I'll be left with x minus 2 here, which is x minus 2 over e to the x if I flip that into the denominator. Now possible points of inflection occur when the first derivative equals 0, or when the second derivative equals 0, or when the second derivative is undefined. Well, this fraction can't be undefined because the denominator can never equal 0. So I do have a critical number here where a possible point of inflection can occur, and that's at x equal 2. So x equal 2 is a possible point of inflection, PPI. The way I check this to be sure is to check it in a concavity chart. So here's x equal 2. Now remember, I want to know the behavior of this function to the right and to the left of this possible point of inflection. So if I plug 3 right in up here into my second derivative, I get a positive value back out. If I plug in 1 up here into my second derivative, I get a negative value. So I have negative and positive. Because I have a concavited change, this is called a point of inflection. If I plug this into my original function, I get the ordered pair 2 and then 2 over e squared for my ordered pair. So what we need to do is take all of this information and graph it. Okay, a couple of important points here. Remember, this is a graph of f of x equals x e to the negative x. So that was our original function that we were trying to graph. If you plug a 0 in for this value of x, I get a 0 back out. So I do have an intercept here. Now, I also had a relative max at 1, and I also had a point of inflection at x equal 2. Well, remember, if I plugged 1 in to my original function, I got a 1 over e back out. So that's this value. This is my relative max. Now over here at 2, if I plug a 2 into my original function, this is where my point of inflection occurs. And let's say here we get a 2 over e squared back out. So I'm going to maximize right through here. And then right at this point I have my negative concavity, and it switches down to positive concavity. And remember, I do have this horizontal asymptote here as well. So here's a nice little curve sketch. If we were to look at this in Maple, let's go ahead and see what Maple would give us. Now, Maple's not going to give us this graph right away, but after we change some of the scales on it, it will look very similar. Okay, here's our Maple graph, and you can see it's kind of hard to see some of the scale here, but you can see we have that same general shape as well. We have our maximum point, we have our point of inflection, and then we also have this trailing off towards 0 but never quite touching 0.